Welcome to video lecture B3. This one is on the null space of a matrix. I'll be your sensei, Tom Roby. Here are the outline and objectives. We'll define the null space of a matrix A. We'll denote it by null of A. And we'll show that it's a subspace. And then we'll connect it with solving homogeneous systems of equations, which is something we've been looking at for a while back in this course. So here's the definition. It's quite straightforward. If you have a matrix A, then you can just look at the set of all vectors that matrix, when you multiply by, gives you 0. In other words, thinking about it in a linear transformation way, it's the set of all things which the transformation A times X sends to 0. Okay? So that's going to be the null space, because it sends things to null. And what's the big property of it? It's just a subset for now. But since I've called it a space, you might guess that it's going to be a vector subspace. And so here's the proposition. For any matrix A, the null space of A is a subspace. And now here, my matrices can be rectangular now. They don't have to be n by n matrices. So I've got these rectangular matrices. And of course, what is the set of all x such that Ax equals 0? Well, it's just the solutions to the homogeneous equations. If we've got m equations and n unknowns, then writing Ax equals 0 is just the way to encapsulate all of that into a single thing. So you see what we're doing here is instead of thinking about solutions to equations as being a bunch of different jumbled things, we've converted them into a single object. So the homogeneous solutions are a single object called the null space. And it's a vector subspace. So the properties that it has are going to come into play pretty soon in this in what's coming up. So, but I know how to check whether something's a subspace or not. Remember, you have to check three things: whether it has a 0. So, is 0 in the null space of A? In other words, is this vector something that when I multiply by A, I get 0? And the answer is yes. Any matrix times 0 is 0. By the way, the null space of A is a subset of Rn, right? Because if I have an m by n matrix, then that means that if you think about it as like taking linear combinations of the columns, then X has to have n entries to be taking a linear combination of n columns. Okay? So the null space of A is a subset of R to the n, which is like the domain of this linear transformation, not the range. Okay. So I don't know, maybe I should draw a little picture down here where I'm thinking about, I've got R to the n here. And I've got my matrix A, and that sends me to R to the m there. And so then the null space is the set of all things that, so I've got 0 sitting inside of here, the 0 vector. So this is the 0 vector in R to the m. But the set of all things that get mapped to 0 by this linear transformation, that's what I would call the null space. So that's my little blobby picture of the null space of A. Okay. So, but why? Let's think about why is this a subspace. So why is 0 in there? Well, because certainly A times 0 is 0. So that means that sitting over in this piece of it, there's definitely a copy of the R to the n 0, just like there's the R to the m 0 over there. Okay. Now, is it closed under vector addition? Is it true that if I have two vectors, x and y, that both get sent to 0, does their sum get sent to 0? Well, that's pretty straightforward, right? Because if if ax equals 0 and ay equals 0, then we know that ax plus y is just equal to ax plus ay, so this will also be 0. Okay? So that means it's closed under vector addition. And similarly, if ax equals 0, then this implies that, then what about a times cx? Well, a times c times x is equal to c times a times x. And so, but a times x is equal to 0, so this is equal to c times 0 equals 0. So there's really nothing exciting going on to show that the null space of A is closed under vector addition and it's closed under scalar multiplication. right? And so let's look at a simple example. Suppose that A is this matrix. This is a 2 by 3 matrix. It's got entries 1, negative 2, 0, 0, 0, 1. Then what does it mean for x to be in the null space of A? Well, to be in the null space means I'm solving the homogeneous system of equations. So you can imagine I augmented it by 0, 0. And so what am I saying? I'm saying this top equation says that x1 equals 2x2. x1 minus 2x2 plus x3 equals 0 just boils down to x1 equals 2x2. And this one says x3 equals 0. Okay? This is all the standard procedure that we mastered already a few weeks ago. And so what does that mean about x1, x2, x3? Well, if x1 is 2x2, then we'll write x1, x2, x3 as 2x2, x2, and then x3 is 0, so it's of this form. I can factor out the x2, and it's x2 times 2, 1, 0. So that's just a line in three-dimensional space along the vector 2, 1, 0. Okay, so that makes sense. That should be a subspace, and it's nice that we've got a description of it. We've got two different descriptions. This is sort of an implicit description of it as being the zeros of this matrix, and this is an explicit description of it parameterized by a single parameter, which I could call k if I wanted instead of x2. But x2 can be any real number, right? For any real number x2, x2 times 2, 1, 0 is a solution to the homogeneous system there. Okay? And just for good measure, let me do one more example, a little bit bigger one. Okay, so here we've got a system of 3 equations and 4 unknowns. So it corresponds to a 3 by 4 coefficient matrix. And since we're only interested in the homogeneous system, we don't really need to augment. We could if we wanted, but nothing would ever change on the 0 side. And so now what happens? We do row reduction. This is actually an example from an earlier video lecture. So you've already seen this example in video lecture E9 or something. So you do row reduction, you end up there, and then you say, okay, so now I've got it in echelon form. I get very simple description of how the variables relate to each other. Namely, this one says that x1 plus x3 plus x4 equals 0. So in other words, x1 equals negative x3 negative minus x4. This one says that x2 equals negative 2x3 minus x4. And then the bottom row says nothing. Okay, so then what? Well, so then that means that I can rewrite x1 and x2 in terms of x3 and x4, just like this. And now you just see, well, what happens? I factor out I split it up into 2 pieces, so I can split it up as a linear combination of x3 times negative 1, negative 1, 2, 1, right? That's what and then negative 1, negative 2, 1, 0, and then plus x4 times negative 1, negative 1, 0, 1, right? And maybe sometimes if I want to, I'll emphasize that x3 and x4 now are no longer variables. They're just free parameters that can be whatever I want. They're free variables. So I'll just call them k and l to think about them as parameters in R. And so what this is saying is that the set of solutions to this equation, which is the same thing as the null space of this coefficient matrix, I can compute explicitly if I want to, using our standard row reduction algorithm. I can compute it as, in terms of this, as the set of all linear combinations, as the span of these 2 vectors. Okay? So take these 2 vectors, take all linear combinations of them, and that's it. That gives me the null space. Okay? So here's a picture that didn't come out exactly as I had hoped. It doesn't look exactly like it does on the screen. But what I mean for this picture to be is just a plane in, well, it's r to the 4 anyway, right? So I'm not going to be able to draw it so well. But maybe if I can complete it a little bit, in the version on my computer, there's a 4th edge here, and this part is shaded rather than black. Okay? So this is what the span of 2 vectors looks like. Even if we're in r to the 4, you could always, because this is just a plane in R4, you can think about it as living in r to the 3 if you want, just by cutting away the dimension that doesn't matter. And so here we've got a picture of this null space of this particular matrix. Okay, so that's the key idea here. Just that the set of solutions to a homogeneous system of equations is the same thing as the set of vectors that get sent to 0 by a matrix, and that is a subspace meaning that it's closed under addition and scalar multiplication, and it also contains 0. So that means that it's sort of the nicest possible kind of set of objects that we want to deal with in linear algebra. And what the picture of such a thing looks like is, a line, a plane, a three-dimensional space, maybe living in some higher dimensional ambient space. Okay, and so that's it for video lecture B3. Thank you for your kind attention.